closely at the architecture of a modern microprocessor. You are staring at billions of microscopic transistor junctions, switching billions of times per second. While these processors perform a vast array of tasks, they do not require a vast library of specialized components. Every operation can be reduced to a handful of repeating patterns. In digital logic, there is a mathematical axiom called functional completeness. It proves that absolutely every possible logic circuit, no matter how intricate, can be constructed using only one specific geometric shape. That singular building block is the NOR gate. To understand how a computer actually processes data, we have to prove how a single primitive logical operation can be stacked to build an entire processing architecture from scratch. The derivation starts with two basic concepts. First is the OR function, where if any input receives a positive signal, the output is positive. Second is the NOT function, an operation that strictly inverts any signal it receives. A 1 becomes a 0, and a 0 becomes a 1. Fusing these two concepts creates a sequential NOT-OR operation. We call it a NOR gate. This diagram shows the standard NOR symbol. The math is expressed as Q equals A plus B, with a bar over the entire expression to denote the inversion. Beside it is the resulting truth table. The logic here is absolute. A NOR gate outputs a 1 if, and strictly if, both input A and input B are exactly 0. Any other combination yields a 0. This truth table is our only tool. Relying entirely on this operation and De Morgan's laws, we will now derive the primary logic suite, NOT, OR, and XOR, using nothing but NOR gates. We begin our derivation with the most vital piece of the system, the NOT gate, or inverter. A standard NOR gate requires two variables, A and B. To turn it into an inverter, we eliminate the second variable by physically wiring both inputs together. As you can see in this schematic, feeding the exact same signal into both terminals means we are calculating A NOR A. By duplicating the input, the logic reduces perfectly to NOT A. We now have a functioning signal inverter built from a single NOR gate. Next, we need an OR gate. This is where rote memorization of textbook logic often creates structural engineering errors. A widely circulated but flawed explanation claims that building an OR gate out of NORs requires 3 sequential gates. The incorrect logic suggests first inverting variables A and B using 2 NOR gates, and then running those inverted signals through a third NOR operation. Let's look at the Boolean algebra shown here. According to De Morgan's law, the inversion of NOT A or NOT B actually yields an AND gate. This 3-gate structure fails the requirement for an OR operation. To build a true OR gate, we must ignore that textbook error and derive the architecture correctly. It only takes 2 gates. Look at the correct 2-gate sequential layout here. We run a standard NOR operation on A and B, giving us an inverted OR. Then we pass that output directly through our newly built NOT inverter. The double negative flips it back to positive OR logic. Deriving functional completeness from first principles is necessary because it exposes the mechanical flaws that blind memorization hides. With the NOT and OR functions secured, we move to the next required piece, the AND gate. To build this, we rely on De Morgan's laws. These theorems act as engines, letting us mathematically translate operations across different types of logic circuits. The specific theorem we need states that the inversion of a logical OR is mathematically equivalent to the logical AND of inverted inputs. Applying this abstract theorem to physical circuit wiring means we have to isolate variables A and B and invert them independently before they interact. We accomplish this by deploying 2 of our single-gate NOT configurations in parallel at the front of the circuit. Once inverted, feeding these 2 signals into a final third NOR gate forces the inversions to cancel out the initial OR operation. Looking at this 3-gate structure, the math holds up perfectly. The final output is a pure AND operation. This demonstrates exactly how we use abstract Boolean theorems to dictate the physical hardware topology of a circuit. The final test of our universal building block is the exclusive OR gate, or XOR. The logic of XOR is highly specific. It only outputs a 1 if the inputs strictly disagree. Mathematically, it isolates the condition where A is true and B is false, or A is false and B is true. Traditionally, engineers build an XOR using a mixed manufacturing approach, combining independent AND, OR, and NOT gates into a single circuit. Our challenge is achieving this exact same highly selective logic using a homogeneous layout of only NOR gates. In this XOR schematic, the first layer splits raw inputs A and B into parallel NOR gates acting as inverters. Tracing the cross-wiring, raw A combines with inverted B at the top, and raw B combines with inverted A at the bottom. These two intermediate gates synthesize the exclusive nature of the logic. By processing the mixed signals, they successfully block identical inputs from passing through. Finally, those two intermediate signals converge into the fourth and final NOR gate on the right. The ultimate output, Q, perfectly replicates the complex XOR truth table, and it does so without relying on a single traditional AND or OR gate. We have definitively proven that highly contingent, complex logic systems can be generated entirely by repeating a single primitive mathematical operation. This uncropped diagram reviews the full scope of our derivation. Starting from a single truth table axiom, we successfully derived the NOT, OR, AND, and XOR functions. But chalkboard mathematics is only half the story. The real application of this axiom lies in the physical and economic realities of engineering. Why would designers intentionally restrict a multi-billion-dollar engineering process to only one gate type? This silicon wafer highlights the physical manufacturing constraints of logic design. Producing microscopic logic gates is an exercise in extreme precision and capital. Relying on a universal gate drastically simplifies the photolithography and semiconductor fabrication process. By standardizing on a NOR architecture, a fabrication facility like this one only needs to tool and manufacture one specific type of physical transistor arrangement. Standardization is the mechanical bridge between a single gate design and the dense, multi-layer grids of a modern CPU. It allows engineers to etch billions of identical microscopic junctions into a single processor die, driving the manufacturing cost of individual logic operations towards zero. The functional complexity of a supercomputer is the result of this primitive logic repeated at the density of silicon. Mastering the NOR gate provides the mathematical framework used to verify the integrity of all digital architecture.